All right, this is section 4.3 for business calculus, and we're going to differentiate logarithmic and exponential functions in this section. So we're going to differentiate the new functions and use their derivatives for graphing, optimization, and finding rates of change. The same rules that we did, or the same uses that we've done with derivatives all the way through the course, we're going to apply those now to exponentials and logarithms. And we're going to emphasize the natural base e, logs, or the natural logs using base e, and exponentials, since most applications are going to use these exclusively. And ignore slide 2. Not sure why I repeated that one. So let's start with logarithmic functions. So the rule for differentiating natural logarithms is right here. The derivative with respect to x of ln of x is 1 over x. So nothing too fancy. So if I look at example 1, I have f of x equals x cubed times ln of x. I have a product rule. We've got two functions there. So when we take that derivative, I'm going to find the derivative of the first one, which is x cubed, which gives us 3x squared, times ln x, plus the first function, times the derivative of the second. And then the derivative of ln x is 1 over x. All right, and then we're going to simplify. The first part of that function doesn't simplify, so we're going to just rewrite it. So f prime of x is 3x squared ln x. And it's important that you're putting anything that's not inside the logarithm in front. That way you don't confuse and don't accidentally put something inside the logarithm that doesn't need to be there. All right, and then on the second one, if I do x cubed times 1 over x, I get x squared, because one of these is canceling with the 1 in the bottom. And that's it. You've taken the derivative using logarithms. Now, what do you do if the top of that is not 1? So if you look at the next slide, if the derivative, or if it's just not ln of x, but ln of a function, that's going to be a chain rule, okay? And what's going to happen is right here, we're going to have the derivative of ln of f of x, anything that's not just plain x, is f prime of x over f of x. Because what you're doing here, I'll show you the breakdown. When we take that derivative, using the chain rule, the derivative of the inside is 1 over f of x. So there's the first part. And then we chain on the derivative of the inside, and we can put it all together as f prime of x over f of x. All right, so that's where that's coming from. So if we look at the next couple of examples, I've got the derivative with respect to x of ln of the quantity x squared plus 1. All right, so again, it's that chain rule. The bottom of our function, or the bottom of our fraction, is just the inside function. So x squared plus 1. The top of that fraction is the derivative of that function. So the derivative of x squared is 2x. And the derivative of 1 is 0. And then you're done. Okay? That's all we're doing. And once we take that derivative, you'll notice that there's no logarithm left. Okay? So when you take the derivative, the logarithm is gone. All right, let's look at the next one. I have f of x equals ln of the quantity x to the 4th minus 1 all cubed. So again, the bottom of that function is x to the 4th minus 1 quantity cubed. The top is taking the derivative of this inside. Well, the inside of this is also a chain rule. Okay, so our 3 comes down, and I have x to the 4th minus 1 squared, and then I take the derivative of the inside, which is 4x cubed, and then minus 0, so I don't need that part. Now we can't leave it here because it does simplify. I can see that x to the 4th minus 1 The 2 on the top cancel out with 2 of them on the bottom. And I can multiply by, I can simplify these two. And I have 12x cubed over x to the 4th. I don't need that anymore. X to the 4th minus 1. And you're done. Now there is actually another way you could have done this. I did the chain rule in the top of the fraction, but if you remember the rules of exponents, and I actually have a mistake here. This would not be equal to each other. I need to have f prime of x in the middle of that, sorry. If you remember the rules of exponents, or not exponents, logarithms, that 3 can come out front, that power rule. So another way that you could tackle this problem, and it doesn't matter, both will work, you'll see we'll get the exact same answer, but another way you could tackle this is that f of x equals 3 times the ln of x to the 4th minus 1. Then we can take the derivative. The 3 is just going to tag on for the ride because it's a constant, so it can just tag on. And then we have x to the 4th minus 1 in the bottom. And the top of that is 4x cubed. All right, so all of this is the derivative of the ln of x to the 4th minus 1. And then we can simplify. 3 times 4 is 12 up top. 12x cubed over x to the 4th minus 1. And you see that we get the exact same answer both places. It doesn't matter which way you do it. I would tend to do the top just out of habit because I wouldn't think about using the power rule, but both are correct and both work. And it's not it's not really a work difference either way. All right. So let's look at exponential functions. Now that we've looked at logarithmic functions, you're going to like exponential functions. Here's the rule. The derivative of e to the x is e to the x. Nothing fancy. The function e to the x is unchanged by the operation of differentiation. And you can see that graphically. If you look at the graph here, remember that your derivative is the slope of the tangent line at a given point. So every time they get to a point, so at y equal to 0, we have a tangent line of 1. Well, the slope is 1. At y equal to 3, the slope is 3. And that works all the way up. And since that always happens, we have a derivative that doesn't change, which is kind of neat. All right, so let's look at an example here. I have the derivative of e to the x over x. Okay, so I have a quotient here, so I've got to use the quotient rule. So remember that quotient rule, the derivative of f over g is f prime g minus fg prime all over g squared. So the derivative of e to the x is e to the x. So I have e to the x times x minus the top e to the x times the derivative of the bottom, which is 1, all over the bottom squared. We can clean this up a little bit, make it look a little nicer. And I have x times e to the x minus e to the x all over x squared. And you're done. Right? Taking the derivative of e to the x is pretty straightforward. On the second one, on b, I have f of x is equal to x squared times e to the x. And we need to find f prime of 1, right? Anytime you want to find f prime of a number, you have to first find f prime. So that's the first thing that we're going to do. So if I find f prime of x, this is a quotient rule, or not a quotient rule, a product rule. So we're going to find the product here, I've got the derivative of the first, which is 2x, times the second, e to the x, plus the first times the derivative of the second, which is e to the x. We can't simplify this any, so we're good. There's our derivative. Now to find f prime of 1, we're going to plug in 1. So I have 2 times 1 e to the 1 plus 1 squared e to the 1, which gives me 2e. And you could put the exponent or not, it wouldn't matter. I'm going to leave it off just so it looks a little neater. Plus 1 squared is 1, so I have 1e. Leave that off. All right. And then we can simplify this and get 3e. You could put this in your calculator and get a decimal if you wanted to, but 3e is a more concise answer. So I'm going to leave my answer here so it's easier. And on like a standardized test, I think you'd see it either way. All right. Now, what if it's not plain x in the top of that exponent? What if it's something else? So again, this is going to be a chain rule. If you have the derivative of e to the f of x, so a function, that derivative with respect to x is e to the f of x, still the same thing, times the derivative of f of x. Okay, so it's a chain rule. We're going to write down the exact answer again and then tack on the derivative of that exponent. All right, so let's try one. In this first example, I've got the derivative of e to the x to the e raised to x to the fourth plus 1 power. So again, when we take that derivative, the exponent comes down, or the same thing copies over. Then we're going to multiply by the derivative of the exponent, which in this case would be 4x cubed. And just like with logarithms, if you're taking that derivative or you're doing anything to that logarithm, you always want to take whatever you're multiplying and stick it in front. That way it looks a little cleaner. And you know for a fact that something you've tagged on isn't supposed to be in that exponent. So I'm going to pull my 4x cubed out front and have e to the x plus x to the fourth plus 1. And you're done. Okay. All right, let's try one more. I have the derivative of e raised to the x squared divided by 2. So all this x squared divided by 2 is in that exponent. So when you take the derivative, when you chain it on of that exponent, it's x squared over 2. So the first thing we're going to do is write the whole thing down again. And then we're going to tack on the derivative. To me, I like seeing it this way a little bit better. So when I take the derivative of x squared over 2, my 2 comes out front. And I have 2x over 2, which reduces to just x. So I'm just multiplying by an x. And again, we're going to pull that x to the front, just so we know for a fact it doesn't go in the exponent. And I have x e to the x squared divided by 2. And you're done. That's it. All right, this next slide is just all the different formulas written out, both your logarithmic and your exponentials. All right, we'll finish up this section in the next video.